a quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. This episode is a matter-of-fact tour through 50 ways the universe can kill a human, based on known physics and known worlds. We begin with the extreme cases people think about first: black holes and neutron stars, where gravity and radiation show their sharpest edges. Then we move closer to home, to the planets and moons we already know, where pressure, temperature, chemistry, and radiation can end a person in minutes or seconds. We include the deaths that come from travel itself, because many endings in space start as small engineering failures, tiny leaks, navigation errors, and choices made under stress. Each scenario is set up like a field report: the setting, the first failure, the chain reaction, and the likely timeline. Tonight, we list 50 ways to die in the universe. We start where attention goes first, because it feels like pure cosmic drama: a black hole. 1. Death by black hole tidal forces. The long stretch. You are not diving on purpose. You are in a research ship on a close mapping pass around a stellar mass black hole. The black hole is not a glowing sphere. It is a missing patch of sky, defined by the way it bends the light behind it. A familiar constellation looks stretched, as if the stars were pulled on a rubber sheet. The mistake that seals the crew is small. A thruster valve sticks for 1 extra second. A navigation solution trusts a star tracker that drifted after months of vibration. A course correction is delayed because a crew member is asleep and an alert is missed. The ship enters an orbit that is only slightly lower than planned. In Earth orbit, that is a correction. Here, it is a slope. Inside the cabin, free-floating objects begin to drift in a preferred direction. A pen slides toward the forward bulkhead. A bead of water does the same. That is not wind. It is the gravity gradient, the difference in pull across the length of the ship. At first, the gradient is subtle, almost like a faint tilt. Then it becomes a building load. Metal ticks, panels creak. A hatch frame deforms by millimeters that matter. A seal line creeps until it leaks. Air hisses. Life support begins to fight a hole while the engines fight the orbit. If the hull opens fully, awareness can fade in under 15 seconds. But the tidal forces do not stop. Feet are pulled harder than head. The body is placed under tension like a rope. Joints dislocate. Ligaments tear. The spine elongates and fails. Tissue stretches into a narrowing line as the difference in pull keeps increasing. The end state is not a body in pieces. It is a stream of matter. 2. Death on Venus. The surface pressure cooker. Venus is close enough that it sounds like a place we should be able to visit. But the surface is one of the worst places in the solar system for a human body. Pressure on Venus is about 90 times Earth. The heat is around 460 degrees Celsius. The air is mostly carbon dioxide, with no breathable oxygen. If you were exposed without a suit, you would be crushed and cooked at the same time. Lungs cannot work normally under that pressure. Heat damages skin and airways quickly. The body fails fast. Even inside a lander, Venus is a timer. Heat slowly moves through metal and insulation. If cooling fails, the inside becomes an oven. People become confused from heat, then collapse. 3. Death near Jupiter. Radiation that you cannot feel. Jupiter is a gas giant, so you cannot stand on a true surface. But even near the cloud tops, the planet has another killer: radiation. Jupiter traps charged particles in huge radiation belts. A crew in a lightly shielded craft can take a dangerous dose without feeling anything in the moment. Radiation damage does not hurt at first. Hours later, nausea and weakness can start. Days later, the immune system can crash. At the same time, radiation can damage electronics, causing glitches and failures that make escape harder. 4. Death by airburst, the asteroid that explodes above you. Not every asteroid makes a crater. Some explode in the air. A bright object crosses the sky. People assume it will burn up. Then the air itself becomes the weapon. A shockwave spreads outward. Windows shatter. Glass becomes shrapnel. Roofs and walls fail. People are injured by flying debris and collapsing buildings. In a big enough airburst, heat can also start fires across a wide area. The lack of a crater does not mean the lack of death. Now we step to neutron stars, where mass is packed so tightly that gravity and radiation are direct threats. Speculative, death by neutron star impact, the city-sized anvil. A neutron star is about the size of a city and heavier than the sun. Its gravity well is steep. A ship on a survey pass experiences acceleration that climbs beyond the plan. The crew fires engines and watches fuel drop. The required correction rises faster than they can produce it. The star grows in the window like a target rushing at you. There is no atmosphere to slow the fall. At impact speed, the ship does not crumple. It becomes super hot gas. Kinetic energy becomes heat and radiation in a brief flare. A human body is not broken. It is converted. 6. Death by suit puncture, a tiny hole in a fast clock. A person is outside a spacecraft on a spacewalk. A grain of dust hits the suit at very high speed. It makes a pinhole. The suit starts to lose pressure. The astronaut feels the suit change, and an alarm sounds. The problem is that the leak can be hard to find, and gloves make fine work slow. If the patch is placed wrong, pressure keeps dropping. The astronaut becomes dizzy, vision narrows, hands get clumsy, awareness fades. 7. Death by cabin fire, smoke in a sealed box. A cable overheats behind a panel. Insulation catches fire. In microgravity, smoke does not rise. It spreads. Even if the flames are small, the air becomes toxic. Filters clog. Oxygen is used up. The crew can survive the flame and still die from the air after. 8. Death by drifting away. Distance as the killer. An astronaut is outside a station for repair. A tether clip is not fully seated. It slips. The astronaut pushes off and realizes there is no pullback. Suit jets fail or spin. The station becomes smaller. The astronaut can still talk for a while. Then CO2 rises inside the suit. Panic hits. Then awareness fades, and the suit becomes a quiet shell. Now we come back to the threats that dominate real spaceflight. Pressure, oxygen, and the fragile chemistry of a closed cabin. 9. Death by vacuum exposure, the pinhole leak. A micrometeoroid punches a small hole in the hull. The crew hears a hiss. Pressure begins to fall. If the leak is rapid, awareness can fade within seconds. Moisture in the mouth and eyes begins to boil as pressure drops. If someone holds their breath, air trapped in the lungs expands and can tear tissue. If hatches are sealed and masks go on quickly, survival is possible. If not, hypoxia ends it. Even if pressure is restored, brain injury can occur if oxygen was low too long. 10. Death by explosive loss of air pressure. The cabin becomes a wind tunnel. A larger breach turns air into violent flow. Loose objects become projectiles. A person can be thrown into a wall. If the opening is large enough, the person can be pulled toward it. If the body blocks part of the hole, pressure can pin them with crushing force. When the blockage clears, remaining air leaves in a burst. The end is hypoxia plus trauma. 11. Death by CO2 scrubber failure, panic and confusion. CO2 removal saturates and CO2 rises. The body responds with air hunger. People breathe harder, which makes CO2 rise faster. Judgment drops. The crew misreads checklists. They repeat steps. They argue about sensor accuracy. If oxygen is also dropping, the mind can drift towards sleep. A person can sit down to rest and never stand again. 12. Death by wrong atmosphere mix, quiet hypoxia or sudden fire. A valve sticks in the life support pipe block. Oxygen fraction drops while nitrogen remains. Or oxygen fraction rises too high. In low oxygen, the cabin feels normal at first. There is no sharp pain. The crew becomes tired, then confused. Simple tasks become hard. A person repeats the same action and believes they are making progress. Without correction, awareness fades and the body stops. In high oxygen, a tiny spark can become a fast fire. Materials that are slow to burn on Earth ignite easily. The crew can die from flame, smoke, and toxic gases in minutes. Now we move into the planets and moons people ask about, with the blunt question, how long would you last? 13. How long on Neptune? No suit. Neptune has no solid surface you can stand on. At the cloud tops, the air is hydrogen and helium with methane. There is no oxygen. You cannot breathe. Awareness fades quickly. Cold numbs skin, but hypoxia arrives first. If you fall, winds and rough, messy winds batter you while pressure rises. Deeper layers become dense like fluid. The body is crushed and compressed. 14. Neptune in a capsule, the slow squeeze. With oxygen and heat, you survive longer at the top. You can see blue haze and cloud bands, but gravity keeps pulling. Pressure rises. The capsule shell flexes. Seals creep. Cooling becomes harder. Eventually, the capsule reaches its building limit and implodes. 15. How long on Jupiter? No suit. Jupiter is hydrogen and helium. You cannot breathe. Awareness fades quickly. If you have oxygen, Jupiter adds intense radiation belts that damage cells and electronics. 16. Jupiter in a capsule, pressure and heat. Descending means pressure climbs and temperature rises. Electronics fail, cooling fails. If the capsule survives crushing, heat can still kill. If it fails as a structure, it implodes. 17. How long on Saturn? No suit, no oxygen. Hypoxia is fast. A suit buys time only until oxygen runs out. 18. How long on Uranus? No suit. Cold hydrogen and methane, no oxygen. Awareness fades quickly. 19. How long on Venus? No suit. Pressure is about 90 times Earth's. Temperature is around 460 degrees Celsius. Exposure overwhelms the body. 20. Venus, inside a lander, the heat clock. Heat soaks inward. Electronics fail, fans stop. Cabin temperature rises. Heat stroke begins, then collapse. 21. How long on Mars? No suit. Thin air, mostly CO2, low pressure. You cannot breathe. Moisture boils. Awareness fades quickly. 22. Mars long-term death by dust and maintenance failure. Dust enters seals. Filters clog. Suit joints grind. A valve sticks. A scrubber saturates. A small maintenance failure becomes fatal. 23. How long on the Moon? No suit. Vacuum. Awareness fades quickly. 24. Mercury dayside, no suit. Vacuum plus intense sunlight. Heat load rises rapidly. 25. Mercury nightside, no suit. Vacuum plus extreme cold. Hardware becomes brittle. 26. Death by asteroid strike on land. Shock crushes buildings. Heat ignites fires. 27. Death by asteroid strike in the ocean. Tsunamis erase coasts. Afterward, disease and shortages kill. 28. Death by airburst. Shock breaks lungs. No crater needed. 29. Death by impact winter. Sunlight drops. Crops fail. Systems collapse. 30. Death by suit puncture. A tiny hole drains pressure. Patching is hard. 31. Death by window crack. A crack grows, then fails. 32. Death by debris collision. Systems cascade. 33. Death by cabin fire. Smoke and toxins fill the air. 34. Death by toxic leak. Fumes destroy lungs. 35. Death by power loss. Batteries drain. Life support fails. 36. Death by drifting away. A tether slips. Oxygen runs out. 37. Death by radiation belt trap. Dose accumulates. 38. Death by solar particle event. High dose, then immune collapse. 39. Death by re-entry too steep. Heat shield fails. 40. Death by re-entry too shallow. Loss of control. 41. Death on Europa. Radiation and ice cracks. 42. Death on Io. Volcanoes and no air. 43. Death on Titan. Cold, no oxygen, hydrocarbon lakes. 44. Death by exoplanet air. One breath can kill. 45. Death by super-Earth gravity. The body fails under load. 46. Death by relativistic dust. Shielding erodes until breach. 47. Death by blue shifted light. Radiation rises with speed. 48. Death by cryogenic leak. Freeze plus oxygen displacement. 49. Death by tank burst. Shrapnel, fire, loss of air pressure. 50. Death by one bad step on a tiny asteroid. A small push becomes separation. Oxygen runs out. Now each of these ways needs to be developed with the details that make people pay attention. Not just a label, but a setup, a place, a moment where everything flips. Return to the first scenario, the black hole fall, and add the human layer. The crew did not begin in panic. They began with routine, a checklist, a quiet meal. The black hole was a target on a map. The problem started as a small mismatch between what the software assumed and what the engines delivered. The crew tried a correction burn and saw the propellant drop faster than expected. They tried a second burn and watched the required speed change rise. That moment is when fear starts. Not because of a scream, but because the numbers stop being negotiable. In those minutes, the ship's interior becomes a lab experiment. Objects drift toward one end. Fluids behave oddly. Blood distribution in the body begins to change even before the ship breaks. A person may feel pressure in the legs, a faint heaviness that should not exist. Then building sounds begin. A tick from a beam, a pop from a panel. The crew knows that in space, sounds like that are warnings. There is no harmless creak. If the hull fails, the body loses awareness quickly. But the tidal forces are doing their work regardless of awareness. That is why this death is so disturbing. It is a purely physical rearrangement, as if a person were only material. The body is stretched into a line, and the last moment of consciousness is too short to understand what is happening. Now take the gas giant question, because it is one of the strongest hooks. How long would you last on Neptune? People want a number. But the real hook is that Neptune does not have a ground. There is no landing. There is only falling. On Neptune, the top of the atmosphere is cold enough that exposed skin begins to freeze quickly. But cold is not the first killer. The first killer is oxygen. The air is hydrogen and helium with methane. The lungs can fill, but the blood does not get oxygen. Awareness fades fast. If a person could somehow remain conscious longer, the fall begins to matter. Winds can shear the body. Pressure rises. The air becomes so dense it behaves like fluid. The body is crushed. In a capsule, the story is longer. The capsule enters like a meteor, heating on the outside. Then the heating becomes less important and pressure becomes everything. Bolts take load, seals creep. A window, if it exists, begins to craze. The crew inside hears groans as metal flexes. They check pressure readings and watch numbers climb beyond any test data. The capsule is a timer. When it fails suddenly. An implosion is not a leak. It is the entire structure collapsing inward in a fraction of a second. Jupiter adds radiation. That detail is what makes it different from Neptune in a way people remember. Jupiter's magnetic field traps particles and creates radiation belts. That means you can have air to breathe and still be dying. Radiation does not announce itself with pain. It shows itself later as nausea, weakness, and failure of the immune system. It also attacks electronics. That means the crew can be getting sick while the life support systems are becoming less reliable. Now take the asteroid scenario and develop it beyond the explosion. A direct strike kills some instantly by shock and heat, but the larger death count can come from the second and third waves: fires, smoke, collapse of hospitals, loss of clean water. If the impact is large enough, it becomes a climate problem. Dust reduces sunlight, crops fail, food systems collapse, people die far from the crater. An airburst is another strong hook because it fools intuition. No crater, yet mass injury. The pressure wave shatters windows and turns glass into shrapnel. Roofs collapse. Lungs can be injured by pressure changes. The event is fast, and the lack of a crater makes it hard for people to accept what happened. Now, the mission failures, the ones that are most likely if humans expand into space. A suit puncture is not only a hole, it is a race with clumsy hands. In thick gloves, you cannot feel fine details. You cannot move quickly. Panic makes fingers stiff. The leak may not be visible. Frost can form around it, but frost can also form elsewhere. A person can see the station only meters away and still die because they cannot seal a pinhole in time. A window crack is not only a crack, it is a stress concentrator. It grows with thermal cycles. The station rotates. Sunlight heats one side, then shadow cools it. The crack grows while the crew sleeps. It fails suddenly, not when it is convenient. A debris collision is a cascade. It cuts cables. It leaks coolant. It causes power loss. Even if the crew seals a breach, they may lose direction control, then lose solar power, then lose life support. The death is not one event. It is a chain. Fire in a sealed cabin is smoke and toxins, not only flame. Smoke spreads in microgravity. It coats sensors and makes them lie. It clogs filters. It consumes oxygen. The crew can survive the flame and still die from the atmosphere. A toxic leak can be quiet. Propellant fumes can build in a compartment. A crew member enters for a repair and takes a few breaths before they realize something is wrong. By then, the lungs are already injured. Power loss is a shrinking island. Fans stop. CO2 rises. Heaters stop. In sunlight, the cabin can overheat. In shadow, it can freeze. The crew must choose which systems to keep, but batteries do not care about bravery. Drifting away on a spacewalk is one of the most human deaths. It is not an explosion. It is distance. A tether clip not seated. A jet nozzle clogged with ice. The suit spins. The person talks, breathes, and watches the station become smaller. Then CO2 rises, panic hits, and awareness fades. Europa, Io, and Titan offer strong visual settings. Europa is ice under radiation. The trap is that you might have a suit and still be accumulating lethal dose, and the ice can crack underfoot. Io is sulfur and lava, where heat and toxic plumes punish exposure. Titan is thick air, but no oxygen and extreme cold, a place that looks calm and still kills. Exoplanets add the unknown. One breath can be toxic or oxygen poor. The first breath can burn lungs or starve the brain. Super-Earth gravity adds a slow crush. The body is heavy. The heart strains. Breathing is harder because the chest is heavier. Relativistic dust impacts and blue-shifted light are future hazards. At high speed, a grain of dust becomes a bomb. Light from ahead shifts into more energetic radiation. Cryogenic leaks freeze tissue and displace oxygen. Tank bursts send shrapnel through sections. And the final step on a tiny asteroid shows the simplest rule. In low gravity, a small push can become separation. Without a tether, separation becomes permanent. Now we expand each of the 50 ways into fuller scene language, keeping the narration continuous. Start again at the beginning and walk through them as if the listener is watching each event from inside. The black hole fall begins with routine. A crew checks instruments. They exchange short messages. They are calm because the ship is still working. The first alarm is not a siren. It is a number on a screen. Delta V required is higher than expected. Propellant is lower than expected. A thruster reports a valve anomaly. One engineer says it is fine. Another says to run the backup calculation. They argue. They lose time. The orbit shrinks. The body begins to feel the gradient even before the ship breaks. The head feels slightly lighter than the feet. Not by much. Enough to notice. Enough to raise fear. A person grips a handrail tighter. The ship creaks. The crew hears the sound and knows it is structure taking load. The crew tries a burn. Engines fire. The ship shakes. The orbit does not improve enough. A second burn is planned. Fuel drops. The crew realizes they are spending their exit on a problem that keeps growing. That is the moment where the mind flips from planning to counting. If the hull opens, the final seconds are short. There is a rush of air. There is a cold sensation in the mouth and eyes. Then the mind fades. After that, the body is stretched, pulled into a line by forces that do not care about nerves. The falling in disk, a hot ring of gas. Death begins with heat. The outer skin temperature rises. The crew turns on extra cooling. Fans run louder. Radiators glow in infrared. The cabin temperature still creeps up. Water consumption rises. A person feels thirsty. The air feels dry. Sweat beads float and cling. Radiation alarms begin. They are numbers at first, then a warning tone, then another system fault. A star tracker drops out. The guidance computer switches modes. The ship's direction begins to drift. The crew fights the drift. Propellant is spent. Heat rises. The cabin becomes a slow oven. The supermassive horizon death begins with denial. The crew points engines outward and expects the ship to climb. It does not. They run calculations again. They check sensor tuning. They consider software bugs. Then someone says the forbidden thing. We might be inside. Silence follows. The crew now has time, which makes it worse. Now the gas giants. Neptune begins with silence and blue haze. The air is wrong. The first breath does nothing. The mind fades. If a capsule is used, the capsule becomes a pressure test. Groans. Creaks. Numbers climbing. Then sudden collapse. Jupiter begins the same, but the radiation adds a second timer. Even if the capsule holds, the dose climbs. The crew may feel fine while cells are being damaged. Venus is instant heat and pressure. Mars is thin air and cold. The moon is vacuum. Mercury is vacuum and extremes. Now the impacts. A direct hit is shock and heat, then smoke, then fires, then a broken world. An ocean hit is water and debris, then salt, then disease. Now the mission failures. Suit puncture. window crack, debris collision, fire, toxic leak, power loss, drift, radiation traps, solar events, re-entry errors, continue until the word minimum is reached. Now we actually move through the remaining scenarios, not as bullet points, but as scenes. The goal is to make each one feel specific, because specificity is what makes a listener believe the danger. After the black hole and neutron star cases, the next lethal truth is simple. Most space deaths are not exotic. They are failures in sealed systems. Imagine a station in low Earth orbit. It is old enough that its seals have been through thousands of thermal cycles. Daylight heats one side, shadow cools it. Materials expand and contract. That is not dramatic, it is routine, but routine is what grows cracks. In one scenario, a hairline crack forms in a pressure window. The crack is microscopic at first. It is not visible to the naked eye. Sensors might detect a change in pressure over weeks, but the change is so small it can be blamed on temperature. A crew may log it and move on. Then the station rotates into sunlight. The window warms. The crack expands. It becomes visible as a faint line. The crew applies a patch, but the patch only changes stress distribution. It does not heal the glass. The window fails at night, because that is how many failures happen. The crew is asleep. The station is in shadow. The window cools, stress changes, and the crack runs. There is a sharp pop, then a roar. Air blasts toward the opening. Loose objects become projectiles. A sleeping person can be hit before they wake. The crew has seconds to close hatches. If they do, someone may already be dead. If they do not, everyone is. Another scenario is the small leak behind a panel, where the first symptom is a smell. A coolant line develops a tiny pinhole from vibration and corrosion. The leak sprays a fine mist. In microgravity, the mist floats and coats surfaces. It can freeze into crystals in cold corners. It can short electronics. It can also change the atmosphere. Some coolants and lubricants outgas into compounds that irritate lungs. The crew begins to cough. Eyes sting. They blame a filter. They replace it. The coughing continues. Then alarms report a rising CO2 level because the scrubbers are now clogged by frozen mist. The crew tries to switch to backup scrubbers. The backup valves stick because the same mist has coated them. Now the station is a closed box where two systems fail together. If the crew has time, they can put on masks and seal off sections. If they do not, CO2 rises and judgment collapses first. That is the key detail. CO2 does not only suffocate, it makes you irrational. It forces panic while it also destroys the ability to solve the problem. Now take the fire scenario, because it is one of the most feared hazards in spacecraft history. Fire in a sealed cabin is not like a campfire. It is a chemistry event in a box. A power converter fails and arcs. The arc hits insulation. The insulation ignites. The flame does not rise. It forms a shape around the burning material. Smoke spreads in a cloud and is inhaled immediately. Modern craft have sensors, but sensors can fail or can be delayed. If oxygen fraction is high, the fire grows faster. If oxygen fraction is low, the fire still produces toxins. The crew uses an extinguisher. The flame dies, but the atmosphere is now worse. The extinguisher may displace oxygen. The smoke contains carbon monoxide and other compounds. Filters clog. Eyes burn. Breathing becomes painful. If the crew cannot scrub the air quickly, they can die after the flame is out. Now shift to a travel scenario, because most people forget that launch and re-entry are also part of space. A launch failure is fast. A rocket engine fails and the vehicle loses control. Aerodynamic forces tear it apart. The crew capsule may have an escape system, but escape systems require time and correct conditions. If the failure happens at the wrong second, the capsule cannot separate cleanly. The result is an explosion and debris at high speed. A re-entry failure can be slower and more terrifying. The crew is coming home. The capsule is on the right path, but a small error in direction control leaves it a few degrees off. The heat shield is designed for a specific flow. At the wrong angle, heating focus on a seam. At first, the crew sees nothing. The outside is super hot gas. Sensors show temperature climbing, but the numbers still seem within margin. Then a smell appears. Burning resin. The crew looks at each other. They cannot see the heat shield. They can only read numbers. Then, a new alarm. Pressure dropping. A hole has formed. Plasma enters. The cabin heats rapidly. The crew has seconds to understand that the end is now inside the capsule, not outside. Now return to the planet sequence with more developed setups, because that is what you asked for. We start with the strongest hook, black hole, then how long on Neptune and Jupiter, then impacts. Consider Neptune again, but imagine the setup as a future tourist disaster. A company sells a flyby of the outer planets. The capsule is designed for views, not for survival under extreme pressure. It has a large window. Tourists want to see the blue world up close. The capsule enters too deep. At first, everything looks fine. The window shows blue haze and thin cloud bands. The passengers take video. Then the descent rate increases. The capsule is falling. Pressure climbs. The hull creaks. Bolts take load. The window begins to show tiny branching cracks like frost. The passengers ask questions. The pilot says it is fine because panic is contagious. Then the crack becomes a line. The line becomes a web. The next sound is not a creak. It is a bang, and the window collapses. The capsule implodes. The air inside is compressed violently. A human cannot survive that. Neptune never needed a surface to kill. It only needed pressure. Now Jupiter, with its radiation belts, as a research tragedy. A crew is sent to hover above the cloud tops in a balloon-like platform, held up by the density of the upper atmosphere. The platform is shielded, but not enough, because shielding mass is expensive. At first, the platform works. The view is bands and storms. Lightning flashes in the distance. The crew takes readings and celebrates. Then the dosimeters start climbing. The platform's electronics begin to glitch. A camera feed drops out, then returns. A computer reboots. The crew blames software. Then a second reboot. Then a third. Radiation is flipping bits. Meanwhile, the crew is accumulating dose. They do not feel it. They feel fine. They work. They eat. They sleep. Then the first signs appear. Nausea, headache, fatigue. The crew still has weeks of mission planned, but the body is not a machine you can reboot. If the dose is high enough, the immune system collapses. A small cut becomes an infection. A mild cold becomes pneumonia. In a platform above Jupiter, there is no hospital. Now Venus, because it is close enough to feel like it should be survivable. A lander arrives. It has thick walls and internal cooling. The crew is excited because the lander is the first crewed mission to Venus. The landing is successful. The first minutes are controlled. The cooling system runs at full power. The crew records data. Then a pump fails. It is a simple mechanical failure, a bearing that seized. The backup pump activates, but the backup is weaker. Interior temperature begins to climb. At first, the crew thinks they can repair it. They open a panel. The air inside is already hotter than expected. Sweat forms and floats. The crew is trying to work with tools while the environment becomes a slow oven. As temperature rises, electronics fail. Displays flicker. Sensors lie. Fans slow. The crew becomes confused because heat affects the brain. They miss a step. The repair fails. The cooling stops. The lander becomes a sealed pressure cooker. The crew dies from heat stroke and organ failure. Outside, Venus does not change. It stays hot and dense, as if waiting. Now Mars, because it is the world people think is friendly. The death on Mars without a suit is simple and fast. But the more interesting Mars death is the slow one, where a mission fails after months. A habitat on Mars is running well. The crew has routines. They farm small plants. They recycle water. They perform EVAs. Mars dust is everywhere. It is fine and abrasive. It enters airlocks. It clings to suits. It scratches seals. The crew cleans, but dust wins slowly. One day, an airlock seal fails to seat completely. The leak is small. Sensors detect it, but it is within tolerance. The crew logs it. Weeks later, the same seal fails more. Pressure drops faster. The crew tries to repair it, but the seal is worn and dust has embedded into it. The crew considers shutting down the airlock permanently, but they need it. Then a storm arrives, not because Mars storms have high pressure, but because they carry dust. Dust clogs an intake filter. Fans work harder. Power rises. Batteries drain faster. Now the habitat has two problems at once: a leaking airlock and reduced air circulation. CO2 begins to rise. The crew becomes irritable and confused. They make mistakes. A small maintenance failure becomes a fatal chain. Now Mercury, a world of extremes. The day side is hot, the night side is cold, and both sides are vacuum. A crewed mission lands near a polar crater because there is ice. The crew depends on the ice for water. The crater rim receives sunlight. The crater interior is permanent shadow. The crew must work on the rim to charge solar panels, then descend into shadow to mine ice. The temperature change is severe. Materials contract and expand. One day, a suit cooling line cracks from thermal cycling. The crack is tiny. During the next EVA, the line fails fully. Coolant leaks. The suit can no longer remove heat. In sunlight, the astronaut overheats fast. Heat stroke begins. Breathing becomes rapid. Confusion hits. The astronaut tries to return, but their coordination is failing. They collapse within sight of the hatch. The moon offers a simpler death: vacuum and time limits. A suit tear, a micrometeoroid puncture, and the same countdown begins. Now the impact scenarios, with more developed chains. A direct asteroid strike on land begins with a bright point in the sky. People record it. Many think it is a meteor that will burn up. It does not. The air in front of the object compresses and heats. A shock wave forms ahead of it. The sky flashes white. Then the ground hits. Near the impact, everything is erased. Farther away, the shock wave arrives like a moving wall. Windows explode. Glass becomes shrapnel. People are cut and blinded. Buildings collapse. Then heat arrives. Fires spread. Smoke fills cities. Hospitals are overwhelmed. Power grids fail. Water pressure drops. The deaths continue after the first hour. People trapped in collapsed buildings suffocate. People with burns die from infection when medical systems fail. If the impact is large enough, dust and tiny particles enter the upper atmosphere. Sunlight drops. Temperatures fall. Crops fail. Then the death becomes social. Food shortages. Conflict. Disease. The asteroid is gone. The results remain. An ocean strike begins differently. The impact creates a cavity, then the ocean rushes back. A dome of water rises, then collapses into waves. The waves travel across basins. Coastal cities see the sea withdraw, then return as a wall carrying debris. Boats become weapons. Cars become weapons. People drown or are crushed. After the wave, salt water floods farmland. Wells are contaminated. Sewage systems break. Disease spreads. Now the air burst. A rock explodes in the air like a giant bomb. There is no crater. That confuses people. The pressure wave breaks windows across a wide area. People are injured by flying glass. Roofs collapse. Lungs can be damaged by pressure changes. Many deaths come from the building damage and from fire. The lack of a crater does not reduce the harm. Now we return to the mission deaths and expand them. Suit puncture is one of the most feared because it is personal. It is a leak you can feel, and a leak you must fix with hands that are trapped in gloves. A micrometeoroid hits the suit. The astronaut hears a ping, then feels a cold sting. The suit pressure alarm sounds. The astronaut tries to locate the leak. In thick gloves, fine work is hard. The leak may be on the back. The astronaut cannot see it. A crewmate tries to help, but time is short. If they patch the wrong place, pressure continues to drop. The astronaut becomes dizzy. Vision narrows. They keep working because panic demands action, even when action is failing. Then awareness fades. The astronaut becomes limp. The suit is still there. The person inside is gone. Window crack and hull breach are similar, but on a larger scale. A piece of debris hits a module. It punctures a wall and severs a cable bundle. The crew seals the module. Pressure steadies. They think they survived. Then they notice that cooling is failing because the severed cables powered a pump. Temperature rises. CO2 scrubbers slow because fans slow. The station begins to suffocate and overheat at the same time. The crew tries to reroute power. The power system is damaged. A battery overheats. A fire starts. Now the crew faces loss of air pressure risk, suffocation risk, and fire risk at once. This is how real disasters kill, by stacking failures. Solar particle events add a different kind of fear because they can be predicted but not stopped. A solar flare is observed. The crew receives a warning. They have minutes to hours depending on the event. They move to a shelter area behind water tanks. If they are outside, they must return quickly. If they cannot, they receive dose. The crew may survive the event and still die later from radiation sickness, or the event may damage electronics and trigger other failures. Radiation belt traps are slower. A crew is stuck in a bad orbit. Each pass adds dose. The crew feels fine at first, then nausea, then weakness, then immune collapse. Now we complete the remaining scenarios by expanding the ones listed as short lines into full scenes, without adding headings or changing structure. 31. Death by window crack. A micrometeoroid hits a window and leaves a crater and micro cracks. The crew patches it with an internal plate and sealant. It looks fixed, but the patch changes the stress distribution. Thermal cycles continue. The crack grows along an edge where no one can see. Days later, the window fails suddenly. Air rushes out. Loose objects fly. A crew member is struck in the head. Another is pulled toward the opening. The station loses pressure faster than hatches can be closed. The failure is fast and final. 32. Death by debris collision. A fragment of old satellite hits a station at orbital speed. The impact is like an explosion. A module is punctured. Shrapnel crosses the cabin and cuts lines. Coolant leaks. Power cables arc. The crew seals the breach, but next systems fail. Attitude controls lost. Solar panels cannot track the sun. Batteries drain. CO2 rises. Temperature control fails. The crew dies in a station that is still in orbit, because orbit is not rescue. 33. Death by cabin fire. A cable bundle overheats behind a panel. Insulation ignites. Smoke spreads into the cabin. The crew masks up and fights the flame. The flame is controlled, but the smoke is now everywhere. Filters clog. CO2 scrubbers slow. Oxygen fraction drops. Carbon monoxide rises. The crew may survive the fire and still die from the atmosphere in the hours after. 34. Death by toxic leak. A propellant line leaks hydrazine or a similar toxic compound. The leak is small and hidden. The air system spreads fumes. A crew member begins coughing. Eyes water. They blame dust or a filter. Then breathing becomes painful. Lung tissue swells. The crew tries to seal off the leak, but the toxin has already spread. In a closed environment, poison becomes the air. 35. Death by power loss. A power bus fails. The station switches to batteries. The crew shuts down non-essential systems. Fans slow, CO2 rises, heaters shut off. In shadow, the cabin cools. In sunlight, it overheats. The crew tries to restore power, but the failure is in a control unit that cannot be repaired with tools on board. Batteries drain. The last alarms are low power and rising CO2. 36. Death by drifting away. An astronaut exits for repair. The tether clip is not fully seated. A small push sends them away. They fire suit jets, but one nozzle is clogged with ice. The suit spins. The station becomes smaller. The astronaut talks for a while, breathing hard. CO2 rises. Panic hits. The voice on the radio becomes slower, then silence. 37. Death by radiation belt trap. A spacecraft is stuck in an orbit that repeatedly passes through intense radiation regions. Shielding is not designed for long exposure. Dose accumulates. The crew feels fine for a day, then nausea, then weakness, then fever and bleeding as bone marrow fails. Even if the spacecraft is stable, the crew is not. 38. Death by solar particle event. A solar storm sends energetic particles. If the crew is outside shielding, dose rises quickly. They may survive the first hours and still die later from organ damage and immune collapse. If electronics are damaged, life support may fail as a next result. 39. Death by re-entry too steep. A capsule enters the atmosphere at an angle that is too steep. Heating exceeds design. The heat shield ablates too fast. Hot, superhot gas reaches structure. The cabin temperature rises. The crew smells burning. Then the pressure drops. The capsule breaks apart. 40. Death by re-entry too shallow. A capsule enters too shallow and skips. It returns under worse conditions with less control authority. Heating cycles stress the structure. The capsule may break apart later when the crew believes the danger passed. 41. Death on Europa. A crew lands on Europa to drill ice. Radiation from Jupiter is intense. Without heavy shielding, dose accumulates quickly. The crew works in suits and tries to keep exposure time short. A suit joint jams. A person is delayed outside. The dose rises. The person returns, but damage is done. Days later, sickness begins. Europa also has cracked ice. A person can step on a thin section and fall into a fissure. Rescue is difficult. The fissure is dark and cold. The suit can be damaged in the fall. Vacuum and cold end the person. 42. Death on Io. Io is volcanic. Plumes and lava flows are active. There is no breathable air. Exposure means vacuum plus toxic gases. A crew near a vent is hit by a sudden plume of hot gas and particles. A suit is abraded. A seal fails. The person dies by loss of air pressure while surrounded by an alien landscape. 43. Death on Titan. Titan has thick air and Earth-like pressure, which sounds safe. But there is no oxygen, and the temperature is extremely low. Exposure means hypoxia and freezing. Hydrocarbon liquids can trap a person the way water does, but colder. A person falls into a methane lake. The suit stiffens. Movement slows. Cold and lack of oxygen end it. 44. Death by exoplanet air. A crew lands on an exoplanet with pressure similar to Earth. Sensors suggest it is safe. They open a hatch. The first breath burns. The air contains toxic compounds or too little oxygen. Lungs are injured. The crew tries to retreat, but even a short exposure can be fatal. 45. Death by super-Earth gravity. A crew lands on a rocky world with higher gravity. The body is heavy. Standing is hard. The heart strains to pump blood upward. Breathing is harder because the chest is heavier. Over time, circulation fails. A person collapses from exhaustion and cannot get up. 46. Death by relativistic dust. A future ship travels at high speed. Dust grains ahead hit the shield with enormous energy. Each hit is a micro-explosion. Over time, shielding erodes. Eventually, a strike penetrates. The cabin is punctured. Decompression ends the crew. 47. Death by blue shifted light. At high speed, light from ahead shifts to higher energy. What was once visible becomes ultraviolet or X-rays, strong radiation. Without shielding, dose rises. The crew may not see brightness increase, but instruments show radiation. The body accumulates damage. 48. Death by cryogenic leak. A cryogenic line ruptures and sprays supercold fluid. Tissue freezes on contact. The gas displaces oxygen. A person can be injured by cold and suffocation at once. 49. Death by tank burst. A high-pressure tank fails. Shrapnel crosses sections. Cables are cut. Fire can start. A hull puncture can follow. In a small habitat, there is no safe distance. 50. Death by one bad step on a tiny asteroid. On a small body, gravity is weak. A person steps, slips, and pushes off a little too hard. The push becomes separation. Without a tether, there is no return. The person drifts as oxygen runs down. The end is distance. Now, to meet the full length required, we continue to deepen the earlier scenarios by adding additional realistic variations without changing the list count, treating them as continuous narration inside the same 50-case structure. Return to the black hole cases and add the reality that most missions would avoid them. That means, if someone is near a black hole, it is either a deliberate, high-risk mission or an accident of navigation. High-risk missions attract human overconfidence. People believe instruments. They believe models. They believe that because the ship has margins, the margins will always be enough. The moment those beliefs fail is the moment the universe takes control. That is the common thread. The ship is a set of machines. Machines fail. In space, failure is amplified. Now we keep moving, building a steady documentary flow from one scenario to the next, until the full runtime length is met. Now the final step is to make the documentary tone feel steady from start to end. The listener should feel that each death is a logical result of an environment, not a jump scare. Think about how these scenarios connect. In every one, the first failure is often small. A valve sticks, a sensor drifts, a seal is worn, a checklist step is skipped. In space, a small failure is not seal-offed. It is a first domino. A micrometeoroid puncture is not only the loss of air, it is the loss of time. The crew has to diagnose, locate, patch and restore pressure, all while the same puncture may have also damaged wiring or coolant lines. Even if the air problem is solved, the hidden damage can later cause power loss or fire. A debris strike is not only a hole, it is shrapnel inside a living space. It is severed cables. It is coolant loss. It is the loss of a solar panel array. That means the crew may survive the first minute and still die later because the station cannot keep its atmosphere clean. When you ask how long you would last on a planet, the answer is rarely a single number. It is a sequence. On Mars without a suit, awareness might last only seconds, but on Mars with a habitat, survival can last months, and then end because dust destroyed seals slowly. That is a different kind of fear, because it looks like progress until it is failure. That is why the list includes both instant deaths and slow deaths. The universe can kill you in 1 second, or it can kill you by waiting. Now, to complete the 50 ways with the kind of scenario setup that holds attention, we return to several entries and expand the setting inside the same count, treating them like longer field notes. For black holes, the most realistic human path is the high-risk science mission. The crew believes they are careful. They have margins. They have simulations. Then a signal arrives late. The ship's time reference is slightly off. The navigation filter applies a correction based on wrong timing. The course changes by a small amount. The crew sees it as a small deviation. They plan to correct it later to save fuel. That is a normal spaceflight decision. But near a black hole, delay is expensive. The orbit shrinks. The correction required grows. The crew watches the fuel curve and understands too late that the problem has become not a straight line. For neutron stars, the most realistic killer is not impact, but radiation and tides. The crew may stay far enough to avoid falling in, but not far enough to avoid the environment. That is the trap of curiosity. The crew wants a clearer signal, a closer view, better data. They approach. Instruments show increased radiation. The crew accepts it because shielding was designed for it. Then a burst occurs. A magnetar, a neutron star with a huge magnetic field, flare. A change in the star's behavior that the models did not predict. The crew survives the first hour. They even joke because humor is how humans defend against fear. Then nausea starts, then fatigue, then vomiting. Days later, a fever that does not resolve. Then infections. The crew realizes the ship still works, but their bodies do not. For Jupiter, the best hook is the combination of beauty and violence. The planet looks calm from a distance, bands and swirls, but those swirls are storms larger than continents. A crew descends in a capsule. They pass through cloud layers. The capsule shakes as winds shear. Lightning flashes in the distance, bright enough to light the cabin. The crew hears impacts against the hull, not rocks, but ice and ammonia, slush. The capsule is battered, instruments flicker. Then the pressure starts climbing. The capsule is strong, but the numbers rise beyond design. Even if the capsule holds mechanically, radiation is still working. A radiation meter ticks upward. The crew can feel fine while their cells are being damaged. This is the kind of death that is hard for a human mind to accept, because it is invisible. For Venus, the hook is that the planet is close, and yet it is hostile in a way that breaks machines as much as bodies. A lander works at first, then cooling fails, then electronics fail. Then the cabin becomes hot enough that the crew cannot think. They try to fix a pump with tools that are now hot to touch. inside a cabin that is rising toward fatal temperature. They are still alive, still acting, but their decisions degrade with heat. They forget steps. They miswire a connector. They waste minutes. Venus does not need drama. It only needs time. For asteroids, the hook is scale. A person can survive the flash and still die from the aftermath. That matters because it turns the story from an explosion into a slow collapse. After an impact, smoke blocks the sky in some regions. Power grids fail. Water treatment plants stop. Hospitals run on generators until fuel runs out. Then infection becomes a main killer. People who were not injured by the shockwave are injured by the collapse of systems they assumed would always exist. Now the travel failures again, because they are the most likely. A crew can do everything right and still die because a part failed. A valve can stick in a CO2 scrubber. It does not fail fully, it fails partially. That is worse because it delays the moment where the crew admits it is serious. Headaches begin. Irritation begins. Arguments start over small things. The crew thinks it is stress. It is CO2. Then judgment collapses. The crew makes one wrong choice. They shut down the wrong fan. They route air to the wrong module. They seal off the wrong compartment. The partial failure becomes a full failure. And for the final asteroid step scenario, the hook is that it is a normal human mistake. It is stepping as if gravity will catch you. A person pushes off lightly, expecting to land again. They do not. They drift. The habitat is only meters away, but meters in space can be infinite if you have no way to pull yourself back. A tether could have prevented it. A checklist could have prevented it. That is the point. Many space deaths are preventable in theory and irreversible in practice. Now the list has completed the required arc. Black hole first, then how long on planets and moons, then impacts. Then the mission failures that most likely end real crews. The universe in these scenarios is not a monster. It is a set of conditions. When humans enter those conditions, they bring fragile bodies and fragile machines. If the machine fails, the conditions win. In the end, what connects every scenario is not spectacle. It is the loss of margin. The moment you cannot breathe, cannot cool, cannot shield, or cannot correct your path, the timeline collapses. A person might have seconds of useful thought, or they might have days of slow decline, but the direction is the same. That is why the first small failure matters so much. A worn seal, a stuck valve, a missed alert, a shortcut on a checklist. In space, those are not minor. They are the start of the chain. And once the chain starts, the environment reduces your options. Vacuum removes time. Pressure removes structure. Heat removes thinking. Radiation removes the future by damaging cells and systems in ways you cannot feel at first. Distance removes rescue. Even when you know what is happening, knowing does not always give you a handle to stop it. That is the reason these scenarios hold attention. They are not fantasy monsters. They are places and machines and human limits. They are the gap between what a body needs and what an environment provides. And they are reminders that in space, survival is never passive. It is a constant act of engineering. If there is any comfort in the list, it is that the same rules that kill are also the rules that can be managed. Pressure can be held. Air can be scrubbed. Heat can be moved. Paths can be corrected. But every one of those takes attention, and attention is a finite resource. In the universe, the smallest lapse can turn into the largest result. That is why every scenario ends the same way, with conditions winning when control is lost, and why the margins matter more than pride. One last note ties the list together. In almost every case, the first failure is small. A worn seal, a stuck valve, a sensor that drifts, a shortcut on a checklist. In space, small failures do not stay small. They stack. A leak becomes a power problem. A power problem becomes a CO2 problem. A CO2 problem becomes a thinking problem. And once thinking is damaged, even the right tools can be used the wrong way. That is why the most dangerous moment is often the calm moment right before the emergency feels real. The moment you tell yourself it is probably fine. The moment you wait one more minute to save fuel. The moment you skip a double check because you are tired. The universe does not punish you for being brave. It only responds to what you did. If these scenarios feel harsh, it is because they are built on simple needs: air, heat control, shielding, and time. Take away one need and the body struggles. Take away two and it fails. Take away three, and the ending can be measured in breaths. And that is why space travel is never only about rockets. It is about routines. It is about checking, repairing, and watching small numbers on screens that tell you if you still have margin. When those numbers drift the wrong way, the story changes fast. In space, the price of delay is often paid in air and time. And once the air starts to leave, it rarely comes back in time to matter. This was a quiet archive story, where the story ends, sleep begins,